now we have the first order Taylor series version. F is convex, so the same as the AP graph is convex. An AP graph, what is AP graph? Is a set. A convex set can be written down by a what? Half space. So this is one half space. This thing, this region, this half space just touch this point. What's next? If I rewrite this half space into function representation, we have this. This function touching the half space, that means this function is beyond the half space, beyond the tangent. This green thing is the function value. This red thing is a strict line at x. What is this? This is strict line, high dimension version. So this is what? Also Taylor series. Taylor series is x plus gradient fx y minus x plus gradient 2 times x. This is a matrix, y minus x, and then y minus x, and then 2, and then you keep going on. If this function is only differentiable one time, then this is gone. Now I'm saying, if this function is convex, we also have this. This is for any xy. Xy can be any value, even xy are infinitely close to each other such that we have derivative. So this red line is a tangent. It tangent touch here. What does tangent mean? Tangent means they touch each other at the point. What point? X. Because when your y is x, you have 0. Then fx is fx. And then this thing have one drawback. You need this to be differentiable. But what if this is not differentiable? This is the starting point of something called subgradient. If this thing does not exist, what are the examples? We have a function that looks like this. We can still use this argument, right? First, this function is convex because of AP graph. AP graph means it can have a half space. Then what? This is a tangent or a support. Support means something below. If this is true for this, now we generalize to this thing, also true. The only difference is at this point we do not have a gradient, but we have something else. We have a cube. What is this cube? Okay, first of all, what is this thing? This is the normal. That means the direction. That means the 90-degree thing to the plane. Now I have this. I also said I have a normal 90-degree to this thing, and I call this q. Then any q that this is true, that means this is true. I just replace this by q. This is now a general version of this, and this is called subgradient. And the collection of all the q that this is true is called subdifferential, and we write this. We will talk about it when we touch non-smooth optimization, but now assume everything is differentiable, okay? So this is the starting point. And here's another thing. This is green, this is red. What happens if I have green minus red? Let's recall what is Cartol derivative. F y minus f x y minus x, okay? This is the fracture, right? And then limit y go to x, right? Now we don't take limit. Because of the figure, this is larger than 0. This part multiply 0, gone. So I have this. Okay, ignore the equality, the norm for a moment. We have this, right? Then this whole thing move to here. This, right? This is the L, right? This is the L. And then what? Then ignore this. This is what? Green. This is what? This is red. This is a straight line, so I call it SX. Okay? I make a mistake. Green on Y. This is straight line, I call it straight line S on Y. But this is under a constant X. X is fixed. So I can subtract this, right? What is this? Well, this is basically just the green minus red, right? Because green is larger than red. So green minus red is larger than 0. This satisfies the first assumption in norm. Norm has to be non-negative. And this also satisfies what? Norm xx is 0. So when y is x, it is 0. So this thing is not a norm, but a divergence. This thing called Bregman divergence, By. So what is this in the picture? This gap. This is Bregman divergence. So this is a y, this is y. So if this y moves towards the x, this is the x, then this gap becomes smaller, 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 and the end is 0. And if this y leaving x, the gap is getting bigger, 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 and bigger. So this Bregman divergence also tells you how bad is this red thing approximating the value of the green thing. Now we talk about the geometry. Now I'm going to get this to this. So I have fy larger than fx plus inner product q y minus x. Then what? I put this to the other side. So fy minus fx larger than this. I move this to here. Now minus means what? Inner product 1, this, right? So this whole thing give me this yx minus each other. This is x coordinate in the x-axis. What is this? The f value minus each other. This is y coordinate. This is a two-dimensional plane. So I have x coordinate and y coordinate. What is this? Q is the slope. What is this? -1. as a y coordinate. Recall one-dimensional calculus. This is slope, right? This slope is positive. This is going up, right? So positive number in the xy plane means we go to here. So what about this? At this point, this is going down. So the slope is negative, right? So this slope is negative. The slope is the q. So we have what? We have something negative. Let's say negative 2. Okay. Let's say this slope is negative 2. And then what's the y thing? Y is negative 1. Okay. So we have a vector like this. Coordinate is 0. X point to negative 2. Y point to negative 1. So this, what is this arrow? This arrow is exactly this arrow. So that means what? That means this line have a 90-degree thing. This arrow is exactly this thing. It's normal to the support. This arrow. This arrow have two parts. The slope, which is here because the slope is negative, and the negative one, which is come from this negative one. This negative one come from this one minus here and then put to here. This connect all the stuff. What the stuff? This is convex if this is convex. This is convex if I have a support. This is convex if this support is 90 degree and then I have an angle like this, which give me the Taylor series expansion of the f at this point. So they are all the same thing. That means what? That means if I put the detail, I finish the proof of 1 imply 2, 2 imply 3, 3 imply 1. But I just didn't do the detail. Okay? And then you may ask, why convex differentiable f you have this? So I just explained to you why this is true, right? Now here's another explanation why this is true. So suppose f is twice differentiable and we just consider one-dimensional problem. So this is Taylor series, right? Alright? Then what? Lagrange remainder theorem, this thing equal to something like this for a middle point theta in somewhere in x and y. We don't care where it is. And because it's convex, this thing is positive definite, so this is larger than 0. This is square, positive, larger than 0. Something plus something larger than 0. Of course, if we remove them, this give us inequality. That's it. This is not proof. Why? Because we didn't talk about why second order derivative for convex function is a positive semi-definite. And then now, this is done. This is done. This is done. Now we have 4, 5. We have this. What is this? We have this 1. What's 1? Fx larger than this. This is subgradient x minus y. What is this? This is exactly this thing, right? I just swapped x, y. So yx, yx now become x, y, x, y. So you see, x, y, x, y. Here is yx, yx. So I want to, what's next? I just add them up. If I add them up, here I have x, y. Here I also have x, y. They both cancel each other, so I have 0. And now I have this. This is just this, right? And what's next? I want this. I just swap. Yeah, it does it. I swap this. Then I get this. So what does it mean? This means monotone. I have, again, a function that is something like this. Convex, of course. Let's say this is R1. Okay. This is also R1. Okay. Now I have a point here. This is 1. This is my x. I have a 3 here. This is my y. Is 1 smaller than 3? Oh, of course, come on. Then this part is fxy. This part is fy, right? This means what? This means if 1 smaller than 3, then fx also smaller than f3. So that's the idea. This is saying that if I have something in domain, this is codomain. Okay, this is f is from domain to codomain, right? If I have a 1 smaller than 3, then the f of this 1 is also smaller than 3. It keeps it. Here's important. What happens if I have 3 larger than 1? This is my x, this is my y. Then I also have f3 larger than 1. Right? So in other words, convex function keep this sign. Then how do I write this thing mathematically? Is to write their difference and then inner product. So if x is smaller than y, this is negative. Okay? And then the gradient, okay, I forgot, it's a slope. Okay? It's also negative. Then their inner product is larger than 0. If x is larger than y, so 3 larger than 1, then the slope is also larger than the previous slope, then this is positive. Positive, inner product, positive, positive. So this is the idea. The idea is, okay, I make a mistake, so this is slope, okay? But anyway, so it's saying that order structure in domain preserved in the codomain, but after taking gradient. So this is the idea. It's like this one have a slope not so steep, this one have a steeper slope, then of course the order is preserved. This one is not so steep because small value, this one is bigger value, so more steep. And this because it's a convex. If I have here, this is my negative 2 and this is my negative 5, then I have the same thing. This is very steep but going down. This is not so steep but going down, but in negative sense. So this is the idea. So this is called monotone. Monotone means what? X monotonically smaller than y, then gradient of x is monotonically smaller than y. That's the idea. A larger than B and A larger than B means AB larger than 0 means A the gap larger than 0. So gap larger than 0 means their product is larger than 0. So we write a gap here. So A larger than B means this GAB larger than 0 is this. So this thing and this thing coexist means they are product larger than 0. So that's why we write the product. And now this G is just greater. That's it. That's it. And this actually is called, which I don't know how to pronounce this name anyway. If I have a function that's convex, then your derivative is always true for this. And this is very abstract. Why? I didn't say what is domain F. This domain F can be crazy thing. So this is saying that if I have a function for some crazy domain, probability measure, topology, shape, or PDE, whatever thing, this is true. But of course, you have to replace this differentiation by the correct differentiation. So this is by this thing. And now this is the big picture. We have a function description of what's a convex function. Is that the convex domain, the domain is convex. This is a function description called Youngson's inequality or chord description. This is convex means this set is convex. This is convex means this set is described by hyperplane. Then this hyperplane go back to the tangent. And this tangent is monotone. Okay? So this is the 1, this is the 2, this is the 3, and this is the 4. And then there's a fifth one. The fifth one is, I didn't have the picture here. This function is a two-dimensional x and y, and you have the z. This function is convex. If I chop it by a plane, then I have a projection onto this plane. If this is convex for any projection, then this whole thing is convex. That's the idea. It's the same as I have a convex set. If I look at it into this projection, this is convex. Then if I do it for any way, this is a convex set. This is the same idea. So therefore, these are the 5 ways you can tell a function is convex. There are actually more than that, but we don't talk about much. And this one is the most useful one. This is for convex function. If we have Taylor series, this is equal for general case. But if we have convex function, we even have this. So that's the detail. Okay?